Hey there, listeners. Ready for another deep dive? Today, we're going to try to wrap our heads around this program someone made, and it's a wild one. It uses quantum computing, some seriously old-school math, and get this, art. Yeah, art. Buckle up, because it's going to be a wild ride.
What really gets me about this program is how it tries to bring these totally different things together, like quantum mechanics and art. It could seriously change how we think about, well, everything.
So, where do we even begin with this? I'm looking at this code here, and it's got all this Python stuff like circ, numpy, matplotlib. I get that programmers use this stuff, but for those of us who don't speak code, could you break it down? What are we looking at?
Think of it like this. Imagine these libraries, that's what they're called, as your tools. So circ, that's like your quantum toolkit. It lets us play around with these things called qubits, like bits in a computer, but way weirder. And then there's numpy. That's the math whiz. It handles all the crazy calculations.
And what about matplotlib? Where does that fit into all of this?
Well, even math geniuses like to see things, right? Matplotlib is like our artist here. It takes all the data and turns it into something we can actually see, hopefully, understand, or at least try to.
Okay, so we've got our tools all laid out. Now, what about this QuantumLanglandsAnalyzer thing? Sounds kind of Star Trek-y, don't you think?
Right. It does sound like something out of sci-fi, but it's actually some cutting-edge science happening right here. This is where the heart of the program is. We're basically simulating a quantum computer.
Right. Okay, I think I'm already a little lost in the quantum weeds here.
Basically, instead of bits, zeros and ones, quantum computers use qubits. And these qubits can be both 0 and 1 at the same time. It's wild. But it gives us a whole new level of power to solve problems that would take, forever on a regular computer.
So we're using the weirdness of the quantum world to do math in a way we couldn't before? It's like upgrading from an abacus to, a spaceship. But I'm seeing all these parameters within the QuantumLanglandsAnalyzer. What are those about? This theta thing, quantum scale?
Think of them like fine-tuning knobs. You got to fine-tune an instrument to get it just right. That's what these parameters do. They let the program tweak things to get the best results.
So it's not just brute force calculation. It's about precision, too. Okay, now we're getting into the Langlands Program analysis part. And things are starting to sound a bit like a really hard math class, like what even are automorphic forms and galore groups?
Imagine a puzzle, right. But the pieces are all jumbled up and you have no idea how they fit. That's kind of what mathematicians have been dealing with for ages. So galore groups, they're like ways you can mess with the puzzle pieces, move them around, but still keep the puzzle itself intact.
Okay, so galore groups are all about transformations. But where do these automorphic forms come in?
They're like patterns. Specific kinds of patterns that show up when you mess with those puzzle pieces. The Langlands program, which is what this part of the code is all about, it basically says there's a connection between these galore groups and these automorphic forms. Like, if we understand one, we can understand the other.
So it's like finding a secret decoder ring for math.
Exactly. And this code is trying to do that using, what else but quantum computing.
This is already blowing my mind, and we're just getting started. What's really cool is how this program takes all this abstract math stuff and makes it real, it turns it into fractals.
That's what's so awesome about it. It connects this super complicated math to something we can actually see and wrap our heads around.
So how does it do that? How do you go from equations and algorithms to art? What's the magic trick?
That's where the LanglandsFractalVisualizer comes in. It takes all that crazy quantum math and turns it into, a picture.
Okay, I like that. But how does it actually work? I see all this stuff about generate points, x coordinates, y coordinates. It's what? Connect the dots on steroids or something?
Pretty much. It uses the results from the Langlands analysis to make a bunch of points on a graph. And when you connect them, boom, fractals.
Okay, now I'm seeing how this whole math to art thing works. What about this? Let's sing some code here, np.csi and np.sinii. That's trigonometry, right?
Yep, sine and cosine. And those little equations, they're what make the fractal look all cool and swirly.
Wait, so we're taking ancient Greek geometry and using it to visualize quantum computer results? My brain's gonna explode.
It's pretty wild, right?
That's an understatement. But this code, it doesn't stop there. Now there's this whole thing about training. It's like we built this amazing machine and now we're teaching it to learn.
You got it. And this is where it gets really interesting. The code takes this test input. They're using the number 42 here.
Why 42? Is that a magic number?
Nah, not really. It could be any number. The point is, the code takes 42, throws it into the quantum analyzer, and sees what comes out. And then it compares that to a target value, like a goal.
Okay, so we're setting goals for our quantum student now.
And then, here's the kicker. It tweaks those parameters, the theta and quantum scale we talked about, to try and get closer to that goal.
So it's like, here's the general direction, now you figure it out.
Exactly. It does this like a million times, getting closer each time.
Yeah.
Each loop is called an epoch. It's basically teaching itself through trial and error.
So it's like artificial intelligence, but for math.
You could say that. And it shows just how powerful these new technologies can be when we use them together.
So where does this all leave us? We've gone from code to quantum craziness to, like, actual art. What's the point? Why did we take this deep dive? Yeah, that's the big question, isn't it? What's the takeaway here? Why is this so cool?
Imagine, like, cracking some of the biggest math mysteries with the quantum computer, right? This program shows us that might actually be possible, you know? It's like we're finally seeing a way to reach the top of this crazy math mountain.
And not just any way, but a path that's, like, lit up with fractals. The universe is speaking to us through math and art at the same time.
It's kind of mind-blowing when you think about it. And it shows how much we can do when we stop thinking about science and art as separate things, you know?
Right, like quantum physics, number theory, computer science, art. They're all connected in this program.
Exactly. Maybe in the future, art will help us make scientific discoveries, and math won't be trapped in textbooks. We'll have code and visuals to bring it all to life.
It's amazing how this program is so complex, but it makes something real, something we can actually see. Makes you wonder what other crazy math art is out there just waiting for us to discover it.
That's the best part about all this, right? Always asking questions, pushing the limits. Who knows what we'll find when we dive deeper into the quantum world and keep exploring math.
Well said. And on that note, we'll wrap up this deep dive. To all you listeners out there, keep those brains buzzing. The world of fractals and quantum mechanics is waiting for you. Until next time, happy exploring.